Hello, we are the East Texas A&M University student team, and our project uses software-defined radios in the music algorithm to create a mobile DOA system mounted on RC cars that pinpoints signal direction with under 2-degree error, beating our 90% accuracy goal. This isn't just theory. DOA estimation drives 5G radar and IoT systems, and our work solves critical hurdles in speed and multi-source reliability. In 10 minutes, you'll see a cost-effective, scalable solution ready to transform wireless tech. Stay to watch live demos and learn how we're redefining real-time signal analysis. Now to introduce our team.
Hello, my name is Ernesto Mateo and my major is electrical engineering, and my assignment was to design the 3D track and the antenna holders and take care of the printing, putting all together, and also helping set up the antennas, and that was my task.
Okay.
Hi, I'm Cameron, and I'm a senior electrical engineer. I was responsible for designing most of the transmit system, setting up so it'd be decently user-friendly for the others to use, and ready for portability on the RC car.
Hello, my name is Brian Palacios. I am a senior electrical engineer. I worked on the music QR code. I made it compatible with the MATLAB and FMCOM5 hardware. I've worked on testing and integration for the two boards, and I also worked on the simulation for the music QR and its metrics.
Hello, my name is Casey Novello, and I am a senior electrical engineering student. In this project, I helped a lot on keeping documentation, recording captures of our progress. I also worked on simulation in MATLAB, along with configuring and help build the 3D printed ULA, A antenna ULA. As we begin to look at our setup, our preferred room setup is a large space room where we can space the table and our receiving antenna array around 11 feet apart from each other. The system consists of two primary subsystems, the transmit and receive. It is designed for azimuth-only DOA estimation using an 8-element linear array, antenna array, and FMCOM5 SDR. Now to go more into depth on the transmit side, for source transmission, we use GNU radio running on two Raspberry Pi devices, which is used in conjunction with two NI USRPs. As shown in this close-up, we can see the USRP connection with the Raspberry Pi, which will be altogether mounted on top of the RC car. Here we are looking at the GNU Radio FFT GUI running on our Raspberry Pi that controls one of our USRP 2901 transmitter. This interface allows us to precisely set and adjust the transmission frequency for our DOA estimation experiments. For our project, we primarily operate at 2.4 GHz, which you can see is currently set as our center frequency. Now watch as we adjust the frequency to 2.403 GHz. This shift is immediately reflected in the FFT display, showing how we can fine-tune our transmission parameters. We are able to do a demo with one or two RC cars. Each of these RC cars will follow a 3D printed track with marked distances, which these distances are then used to calculate the actual physical angle of the antenna. Now moving over to the receive side, our receiving subsystem uses an 8-element ULA, which is designed for azimuth-only DOA estimation of up to ± 90 degrees. The signal reception and processing are performed in real time by two FMCOM5 platforms, each integrated with an AMD baseboard. The data received is transferred to a host PC running MATLAB, where the music music algorithm with QR decomposition executes the DOA estimation. Next, let's break down the system's workflow. Signals are captured by the dual FMCOM5 platforms, processed instantly by the AMD hardware, and streamed to MATLAB. At the top, you can see how the antennas receive signals to be used by the FMCOM5 board. Now let's take a moment to look at our 3D printed 8-element uniform linear antenna array. Each of the antennas are spaced at λ/2, where lambda is the wavelength corresponding to 2.4 GHz carrier frequency. The element spacing is adjustable for any carrier frequency of interest due to how the 3D parts are printed on the array. In this next clip, we are going to see our system in action. We'll start with a single source scenario. We'll place the RC car with the transmitter at a node position, and you can see on the display in our MATLAB that our system estimates its direction with high accuracy. The spatial spectrum shown on the screen has a clear peak at the transmitter true angle. For this next system, what you will see is our real-time DOA system tracking a moving RC car with an RF transmitter. We'll start the transmitter stationary at around 0 degrees to establish a baseline. Notice the stable DOA readings on the display. Now I'm moving the car to the left. Watch how our system tracks this movement in real time with the DOA angle decreasing smoothly as the car moves. I am stopping at approximately -30 degrees. See how the DOA estimates quickly and stabilizes at this new position. Now I'm returning the car to its original position. The DOA readings are increasing as expected, tracking the rightward movement. And we are back to the starting line. Some key accomplishments we've achieved while doing this project is that we have successfully implemented a real-time DOA estimation system capable of accurately tracking RF sources. Our music algorithm with QR decomposition demonstrates consistent performance with low computational complexity. We've achieved standard deviation under 2 degrees and have an accuracy of within 2 degrees. The system has been validated both through extensive MATLAB simulation and real-world testing, and we developed a complete software framework for data acquisition, processing, and visualization, all optimized for our specific hardware configuration. Throughout this project, we've encountered several significant technical challenges during implementation. The most prominent was severe multipath interference in smaller testing rooms, which degraded estimation accuracy. To address this, we conducted our tests in larger rooms as seen in the demo, and we've done our tests outdoors. Other challenges was the lack of phase synchronization between our FMCOM5 boards. We addressed this through our novel cross-correlation approach rather than requiring hardware modification. Moving forward, we've seen several opportunities for improvement. First, testing in an anechoic chamber would allow us to better characterize system performance without multipath interference. Second, implementing external local oscillators synchronization between the FMCOM5 boards could enhance phase stability and improve multi-source resolution. Finally, we'd like to extend our system to perform 2D DOA estimation by adding elevation angle detection. Thank you for your attention. We're happy to answer any questions about our implementation or results.